So we're temporarily back from our coronation, and thought I would try to start getting in a few more of the units that I had missed before we left school. We're going to begin, and so we're going to pick up partway through the course because I jumped around a little bit, and we're going to take a look at what I call Unit 6, and what I cover in Unit 6 is the idea of multiple bodies. In other words, I'm talking about systems. Kind of a lot of different ideas are captured here. I define a system as multiple objects moving together. Now, if you think about it, everything is a system. Everything, this marker, is made up of many objects, many bodies, and they're tied together. It's made up of many molecules. These molecules are tied together somehow, and so all the molecules in the marker itself that moves as a system. And so that's one thing I try to reinforce, is that when we looked at, like in projectile motion, a ball, yeah, that's a single object, but that's also a system of many different objects tied together. And so try to make this idea of a system a little bit less confusing. So a couple of questions that I want to pose. The first question is, what affects the motion of a body? Just a single object. And obviously, by now we should recognize that the answer would be outside forces, or an outside force, either one. We can ask the same question: what affects the motion of a system? We have the same answer, and outside forces. So we're not really changing anything, we're just expanding our definition of a body. A body is no longer a singular object, it's a bunch of things that are tied together. They're connected, they're linked together somehow, and they're moving together. So, as I like to do whenever I introduce a new unit, and this is the introduction to Unit 6, I like to talk about the big ideas, forces, energy, and motion, and basically give you the end of the story answer. So, in regards to forces, what we know is that the motion of a system, and here's where I like to kind of throw in the idea of center of mass. The motion of the center of mass is based only on the net external force. Based on net external force and the mass of the system. Because remember, acceleration is force over mass. So we have to look at the net external force, because internal forces don't count, don't matter, they're not going to affect the motion, only external forces, and then the mass of the system. And that's the other thing. Internal forces don't affect the motion. If internal forces don't affect motion of the system. So, if internal forces affected the motion of the system, I could simply make myself move without any force being applied to me. You know, I could just think, okay, I'm going to start moving, and my legs can start moving, but there has to be an outside force that actually allows me to move, like the force of friction on my shoes from the floor. And so this is a pretty important idea to keep in mind that often gets challenging to understand. And so let's take a look at the idea of energy. And this gets into a somewhat different idea of system, and that is gravitational potential energy is stored in the system. Now, what I mean by system here is a little bit different, or could be different, than this idea of a system. This idea of the system is like a ball, multiple things tied together. This idea of the system, we're looking at the system like of the ball in Earth. And so this is one of the ideas that get a little confusing, because the word system can, I don't want to say mean two things, but it kind of can. And so this is one idea, and I didn't have a better way to address it, and so I tried to address it this way. If the system is closed, we have conservation of energy. We have, if the system is closed, there's no external forces. If there's no external forces, there's nothing that can change the motion of the object, and so energy is going to be conserved. Our big ideas with momentum are similar. If our net external force is 0, then the change in momentum is 0 for the center of mass. In other words, we cannot change the momentum of the center of mass of the system if the net external force of the system is 0. Similarly, as with energy, if we have a closed system, momentum is conserved. So, again, these two ideas, for these two ideas, energy and momentum, the system I'm referring to is a little bit different than the system here for the forces. Let me take a second and just kind of illustrate an example of what I mean by that. I was going to give an example of the two different types of systems that I was just talking about. I think what I want to do is first talk about the idea of center of mass, and then we're going to give the example, because I think that will better help understand the idea of the system a little bit better. So, center of mass. College Board likes to use this phrase a lot. Sometimes it gets really confusing. It truly shouldn't be. But it's confusing because a lot of times we don't use it often in class, and I try to use it more. But basically, the center of mass is the point where all the mass of a system can be considered to be located. I've got a lacrosse ball. It's rubber, it's solid. It's got what we call uniform mass, meaning if I cut it up into equal sized volumetric pieces, every piece is going to have the same mass. So it has what we call a uniform mass distribution. And typically that's the only type of objects we're interested in this course. And so it's solid, it's uniform, and we can treat all the mass of this lacrosse ball to be located right smack dab in the center of the ball. Great, that's what I mean. It can be considered to be located. And when it's a nice uniform mass distribution, and when it's nice and solid, it's in the geometric center. Now, next example, a tennis ball. A tennis ball can be considered uniform, except it's a shell. There's nothing in the middle. Yet, the center of mass, we can consider all the mass for the tennis ball to be located right smack dab in the middle of the tennis ball, even though there is nothing. And so this is a little bit confusing. When we're dealing with a uniform mass distribution, the center of mass is at the geometric center of the object, even if there's nothing there. And so let's say we have a bowling ball, geometric center, nice and solid. Tennis ball, geometric center, even though it's a shell. A hula hoop, geometric center, even though it's a round shape and there's nothing in the middle. Now, if it's not uniform, so if it's not uniform, we have to figure it out. Center of mass needs to be determined. Now, and here's the thing. The calculation can be really actually quite complex. We're not going to actually get into that calculation a whole lot, but you do need to be able to look at a situation and qualitatively say the center of mass is located right about here, and that'll work pretty well. Let me give you an example of that. So an example of center of mass. It is very common when stars form that they actually form in pairs. And so we have two stars that form near each other, and they're gravitationally bound to each other because they're close enough. And let's say that that each star has the same mass. And so I'm just going to make a connection between them, and that connection represents the gravitational force that holds them together. And so these two objects are tied together. A lot of times it's two masses connected by a light rod or a string. Fine, it doesn't matter. And if these two masses, if these two stars are the same, have the same mass, then the center of mass of this system, this is our system, the center of mass of the system is located right between them. It's almost like the balance point. And that, I guess you consider center of mass a little bit like that, the balance point. If one star was twice as big as the other star, the center of mass is going to be shifted a little bit. And so if you think about the balance point or a teeter-totter, the center of mass isn't going to be right in the middle. It's going to be shifted maybe over to here. And we can actually figure out the exact location, and it's not necessarily a hard calculation. It's just, I don't know if it's necessary, and sometimes I do it in class just to show it, but I usually don't ask the kids to do it. I just want them to be able to qualitatively say, here is about where the center of mass is. So, that's what I mean by center of mass. This is a system. Two objects tied together. This would be a system. And so in my definition of forces, when I talked about system, this would be what I'm referring to. Let me finish. I want to finish looking at a center of mass example, and then go back and look at my example that I want to give you for systems that I talked about a few minutes ago. I have an example that I use in class that illustrates how the center of mass of a system is not affected by internal forces. That the motion only depends on external forces, and it involves a man on a canoe. I'm going to go to a PowerPoint or to my Smartboard presentation to illustrate that, because if I try to draw it up here, it's going to look really poor. So let's go to that real quick. So I'm here at my computer to illustrate the fact that the system center of mass motion does not change when there's no external forces acting on the system. By using this example that I use in class, it's easier to see it here on my computer screen than trying to draw it up on the board. And what we have is we have a man standing on the canoe, and the canoe's on water, and so we have a frictionless surface between the canoe and the water. And what we're going to do is this man is going to walk
to the other end of the canoe. Now, let's just say that the man has the same mass as the canoe. And so here's the center of mass of my man, along right at this point. The center of mass of the canoe is right in the middle. And if the two have the same mass, then the center of mass of the system is going to be right smack dab between the two. So right here, it's the center of mass of my system. And if the canoe is at rest, as the man walks that way to the other end of the canoe, the center of mass of the system will remain at rest. And that's the whole idea that we're trying to illustrate. So the guy starts walking towards the other end, and when he's partway to the other end, this is what we have. He stops in the middle of the canoe. His center of mass is right below him. The canoe's center of mass is right below him. So the system's center of mass is right here. They're all at the same spot. Great. But you got to understand that as the man is walking that direction, he's going to push the canoe that way. And so his center of mass moved. The canoe's center of mass moved, but the center of mass of the system did not move. And when we get all done, we're going to look at the big overall picture. So the man keeps walking towards the other end of the canoe, and pretty soon we're in a situation that looks like this. Here's the center of mass of the man, center of mass of the canoe. The system's center of mass is located right in between them again. And so what you have to understand is, if you look at the big picture of all that has happened, it looks a little bit like this. As the man was walking this way, he pushed the canoe in the opposite direction. So as the canoe's center of mass moved to my left, as the man's center of mass moved to my right, the center of mass of the system, though, did not change position because there's no external forces acting on the system. And then as the man continued to move to the other end and his center of mass moved, the canoe continued to move the opposite direction because he's pushing it. The center of mass of the system remains in the same place. And the center of mass of the bodies in the system can change, because there is an external force on the man. There is an external force on the canoe. The man's pushing it. The same thing, the canoe's pushing the man. But on the system, there's no external forces. And because of that, the center of mass of the system does not move. The center of mass of the individual bodies may. This is a real, I think, a pretty important idea when we're talking about center of mass to be able to recognize.
So I'm going to call this my systems examples. Let's say we're on top of a cliff. And we have a ball. No, we don't have a ball. We have two balls. And so we have a picture of a ball tied to another ball. And what we're going to do is we're going to throw this ball off the cliff. And it's going to look something like that. It's going to be a projectile. If the balls have the same mass, the center of mass is right in the middle, and we can model the projectile motion of this ball, of these two balls, based on the center of mass. We can model the projectile motion based on this system. So this is the forces acting on the system. When we're talking about energy and momentum, I've got the ball here, and it's probably spinning. I'm not showing it that way, but and so we have the ball going through the path. When we talk about the system, when we talk about energy, when energy is conserved, and when momentum is conserved, and I'm just going to focus on energy, we're looking at the system of the balls that are tied together and the Earth. And so this is what I was referring to as my little microscopic system, so to speak. When I look at the system for conservation of energy, I'm looking at the system of the Earth and the balls, because here is where the gravitational potential energy is stored. When I talk about the energy of a system, I'll talk more about this idea right here. But you see, and this is what I was referring to, there's two different types of systems. On the forces, this system, this is the force system that I'm dealing with on forces. A lot of times when we're talking about energy and momentum, I'm looking at this type of system. I'm looking at the ball in the Earth, for example. I'm looking at all the objects that play into the motion of these two balls tied together. And of course that has to include the Earth because gravity is pulling it down. It can be a somewhat of a confusing topic because this term system means several different things, but it's really important to understand, and as I go through the rest of this unit, hopefully that'll make more sense.